this class to learn about stars and planets and stuff like that. So I'm saying, self, why would you go ahead and put this stuff in there about atoms, and then we just had one slide about molecules. You know, you have to need both about electrons and protons and neutrons. And why do they need to know this stuff? Well, actually, in order to kind of understand what we're going to talk about, how the planets formed a little bit, how our sun formed was just a star, we kind of need to kind of know some of these basic things. So there's a lot of conservation themes in our universe. There's the conservation of momentum. Okay, there's the conservation of energy. There's the conservation of matter. What's that? Oh. So these things can be, these different types of energies can be converted from one energy to another, okay, but they have to be tracked. Energy can be consumed as it does work, but it's always trackable. Thank goodness, right? I want to spend a little bit of time talking about stored and versus potential energy coming up. But before I do that, I want to talk about this. So the other day, what's the three pieces that make up an atom? What's in the center? Neutrons and protons. And then electrons on the outside. Very good. Of those three subatomic particles, the electrons are they make me itch sometimes when I think about them because they have that buzz thing going. They have a lot of what's called kinetic energy. Kinetic energy is energy associated with motion. And the electrons kind of have that all going on. Now, all matter, whether it's, all matter, don't pull back the atom now, not just the electron, but all matter has motion. It has kind of this buzzing motion we call vibrational motion. It has what we call translational motion. It kind of moves from point A to point B. It has rotational motion. All matter has motion. But the hotter it is, the more motion it has. That's just it. The hotter matter is, the more motion it has. When I say hotter, I'm saying you jack up the temperature. So here we have, can you see, I'll call this one A. I'll call the left one A. And the right one B. Now, I don't know if you can see it from there, but the lengths of the arrows that's showing you motion, by the way. Those little balls are matter. And it's showing you motion. How many people, and the length of the arrow is showing you how much motion is. So how many people think that A has more motion? How many people think that B has more motion? You're right. Very good.
It's like ants in the cold.
it's like ants.
But in the heat, they go real quick.
I've heard another student not that long ago told me it is just like ants. If you buy ants in the wintertime, when you finally get ants in the mail, they're all so sluggish. You're like, oh, my ants are dead. But if you let them come up to room temperature, then they just crawl around. Yeah, it is definitely like that. So this is what we have going on. Now, when it comes to energy, we're all about, quantifying. We're all about saying, how much energy is it? Well, energy depends upon how fast they're going. So, yeah, you guys told me these are going faster. It's at the higher temperature. Not only that, but it also has to do with what we call kind of the mass, or how densely packed those particles are moving at that temperature. Okay. So this is to say that what if we have two chunks of matter? Those little balls are moving particles, moving matter. Okay, which particle, A or B? So we have liquid water here, and we have gas over here. Okay, how many people think that A is the particles are moving faster? How many people think that B, the particles are moving faster? Very good. So they're moving faster. They have a higher temperature. Each individual particle has more kinetic energy. But which one, A or B, has more particles per volume? How many people think A has more particles per volume? Exactly. That's my point. Is when it comes time to saying how much energy either that pot of boiling water has at 100 degrees or that gas that's in that oven has at 200 degrees, we also have to consider the number of particles that have that kinetic energy. So I think my caption is that it's quite possible, it says, but the water contains more thermal energy even though it's slower because they're more packedly tied together. That's all. So again, kinetic energy associated with motion. A lot of times you kind of already knew that when you came into this class. And all matter has motion, so all matter has kinetic energy. And what happens when you slow matter down? The motion? It's less. The motion is less, and the kinetic energy is less. Some of you who have taken physics know, and I don't know a lot about physics, but KE stands for kinetic energy, and one way to calculate it is 1/2 mv raised to the second power, or squared. So of course, as we cool it down, our velocity decreases and our kinetic energy decreases too. So those are just kind of some things to think about. All matter has motion. Now, kind of related to that are these 3 temperature scales. So if you're like me, you might have asked your Alexa what the weather was going to be like, and she told you what the weather was going to be like in degrees Fahrenheit. Okay, this is English system. Oops. Of course, Celsius is metric. Now, this you may or may not be as familiar with, the Kelvin temperature scale. The Kelvin temperature scale is also metric, and it's a fancy temperature scale. It's the most sophisticated. What makes this metric scale more sophisticated than the Celsius metric scale is if you have 0 units on the Kelvin scale, it actually means something. So what is 0 Kelvin? First letter A, it's on the slide. It is absolute 0. Yep. 0 Kelvin is absolute. I'll put ABS for absolute 0. Exactly. It's absolute 0. And as you guys were telling me, as something cools down, it goes more slowly. And at absolute 0, it has no motion. Now, in science, we kind of chase down things. We kind of put out, gosh, it's been so long, but we put out rules. Rules of our universe is that all matter has motion, and here I have matter that has motion, no motion. Well, that's a conundrum. And so, as it turns out, and this is one you're going to be challenged. You're like, oh, are you sure, Mrs. Snipes? But nothing has been cooled down to absolute 0 because it violates the laws of this universe, the law of thermodynamics, or law of molecular motion, kinetic molecular theory. All that has motion. There was a few years ago now, maybe, folks that published a paper in a science journal, physics science journal, I'm sure, that said that actually they took matter and they cooled it down below absolute 0. But if you look at their data, they kind of took an average reading of things and kind of said, kind of a bell curve thing, and said, well, on average, then it was less than 0. One of my pet peeves, and I haven't followed this up, but we went to, anybody here been to, maybe want to go get to this class, the Chicago Planetarium? Cool, like Michigan. Take the train. It's a possibility. The train's pretty inexpensive. So the planetarium's a great place, and it's kind of broken up into chunks, and one of their chunks is about the planet. And one of my pet peeves is they said what temperature each planet was. So I'm like, well, that's pretty cool. But each of their placards for how cold the planet was, it went down to, I took a picture because I was so upset. On the scale, they showed, I can't remember what 2, or maybe they showed all 3 of these scales, but on the scale, they actually showed it to like a negative 100 Kelvin. And I was like, dude, stop it. That just really upsets me. Don't even show that on the scale. Anyway. So what is this last, it used to be a planet, now it's called a dwarf planet? Pluto, yep. Pluto has different regions with regard to temperature, and it runs about 9 or 7. And we don't use the word degrees with Kelvin. 9 or 7 Kelvin units. So 9 or 7 units above 0. Okay. Anyway, the other cool thing, or a cool thing, like if in your science, and you have to kind of go back and forth between these 2 metric scales, they are offset by 273.15 units. The unit on the Celsius is equal to the unit on the Kelvin. They're just offset. So that's kind of, and you can actually see that right here. They're offset by 273. So that's kind of nice going back and forth. Anyway.
What's a high for Pluto?
The high for Pluto, I can't remember, did I tell you, it's probably, I think I said 11 or 12 Kelvin. So, you figure freezing is 273 Kelvin, freezing of water, because water freezes at 0 Celsius, 32 Fahrenheit, and 273 Kelvin. When we get to talking about how hot a star is, we're really going to use the Kelvin scale because it's kind of nice. the surface of our sun, now the center of our sun is a lot hotter, but the surface of our sun runs about 6,000 Kelvin. So kind of put this in perspective. Very good. So I said a few slides ago that energy can kind of go back and forth. We can take radiation energy from the sun and we can convert it to electricity. I know with everything that's going on with regard to the catastrophes and natural disasters, it's too bad that, you know, and I know it's hard. It takes a lot of money to put into having solar energy, but if they had solar energy, then maybe individual things wouldn't be so bad. But anyway, you can go back and forth with the different energies. We can go back and forth between kinetic energy and potential energy. So kinetic energy is associated with motion, okay, and you can kind of see that motion with this ball, okay. Potential energy, a good way to talk about it is kind of the energy of position. So as I don't think this will break, this is pretty solid. As I hold this up here, the potential energy it has is related to, actually, I'll back it up here. You won't have to use this, but PE stands for potential energy, and it's related to its mass, the acceleration due to gravity, and how high it is, okay? So that's kind of how that goes. So if I would put it higher, then it would have more potential energy. Okay, if I make it more massive, it has more potential energy, that sort of thing. So it has all this potential energy, and as it falls, of course, we talked about how fast it's going to fall after 1 second. 10 meters per second, very good. After the second, 20, third second, 30. Yep. It's going to keep picking up 10 meters per second each second it falls. So it's going to go ahead and do that sort of thing. Now, that was pretty fast, but when it's down there, how much potential energy does it have? 0, because its height from falling is 0. And you might say, well, it has, like that, it has 0 potential energy, 0 kinetic energy. And this gets kind of a little bit, but actually as it fell, it imparted energy to this lovely floor we're walking on. Not that the floor really needed any more energy. So that's where that energy went. It's always conserved. But if I could kind of stop it here anywhere, you'd say it's going faster, faster, faster. Its velocity is increasing, so its kinetic energy is increasing, but its potential energy is decreasing. So it's a trade-off. So there's that. Now, keep that in mind, and we're going to switch gears to something a little more astronomy-ish. I don't know if that's a real word or not. So we still need to, oh yeah, your unit exam. Your unit exam in here is got to be, because we've got to do something to get off of Unit 1, it's going to be a week from Monday. So Unit 1 exam, I told you I would tell you, and commit, is Monday. Somebody help me out. What is the date Monday? A week from this Monday. Is it the 24th? 24th? Okay, thanks. So Unit 1 exam, Monday, September 24th. Got to do it.
I think it's 25th.
Thank you.
Oh, I'm sorry.
Thank you. Thank you for all. 25th. Very good. That's when it'll be. Okay. So I'm liking that because that'll give me this weekend to kind of get the test together. And then from the test being together, I'm going to give you a review sheet. And I'll probably this semester just put together a review video, push it out there so you can watch it or not watch it. Hot all of a sudden. Okay. So any questions about the unit exam? I'll be talking more about that next week. What I started to say is one of the things I want to get through in Unit 1 is this idea of kind of the general formation of dun, 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 the sun and the planets. And what we're going to do is start out with the sun and the planets basically being kind of a cloud. Yes, ma'am?
I missed what the MGH stands for.
Oh, M is mass, and G is the acceleration due to gravity. So I'm just going to say, yeah, I'll just put A for acceleration due to gravity. And as you guys were kind of talking me through it, you guys told me that acceleration is approximately 10 meters per second for every second it falls. So 10 meters per second, or 10 meters per second squared. And then H is height. Thanks for asking. So that's the conversion of potential energy to kinetic energy, is something called. But here with our system of sun, which is a star, our star system, star with planets. Do most stars have planets? Yes, and that will be a test question of sorts, somewhere. Okay. So it actually started out as what we call a nebula. I'll go ahead and put the word up there. See, I don't think it's on there. Nebula. That's what that is. It's just a cloud into outer space. We're going to call it the solar nebula next week, but nebula, that's a cloud. So here we go. As the nebula is nice and kind of spread out, it has a lot of potential energy, but not much kinetic energy. Not much kinetic energy. What do you think about the temperature inside the nebula? It's colder, yeah. Kinetic energy, low kinetic energy, low temperature, exactly. And when we talk about star formation, let alone our sun formation, we're going to actually, I think, touch on how does this happen. And as I'm doing this, I'm trying to show kind of a contraction process. There are different ways to stimulate a cloud to become contracted. But if you buy this, as it becomes contracted, it has less potential energy, and kind of like our falling stylus there, as it has less potential energy, it has more kinetic energy. And that kinetic energy is manifested in the form of temperature. My whole point is it contracts and heats up. Clouds do that all the time in our atmosphere. Okay? So contraction heats up. Less potential energy, more kinetic energy. So I'm about done. Because one of the things about stars, including our sun, is, by the way, do you remember how hot in Kelvin our surface of our sun is?
6,000?
About 6,000 Kelvin, very good. If you go to the center of our sun, it's like 1,000,000 Kelvin. It's very hot. It's very hot. We'll see what that temperature is coming up on a slide, later on in the slide. But my point is, it's very hot, and that heat actually came from the conversion of potential energy to kinetic energy. Okay, so that's all of it. And in order for a star like our sun to turn on, it needs to be hot enough and dense enough to begin what we call nuclear fusion. And actually, that's kind of coming up in my last slide. So that's all that is. All right. Nuclear fusion. So you guys told me this morning that we have protons and neutrons in the center of an atom and electrons outside. And I don't know if you guys remember on Wednesday, what particle did I say of those three actually identifies what element an atom is? You remember? The electrons, the protons, and the neutrons. It is the protons. Yep, the protons. So we have this thing called nuclear fusion, and what's happening in the sun, in the center of our sun, is it is taking an H, what does that element does that stand for? Yep, and it's a little more complicated than this, but taking a hydrogen, and it is forming, what does He stand for? Helium, yep. So that's what's going on in the center of our sun. Okay, and again, we'll talk more about this. But if you were to weigh this right here, I'm going to call this M1, if that's okay for you, the mass of what you start with, and I'm going to call this M2 over here, the mass of what you end with, okay, you're going to find you lost a little bit of mass. So I guess writing as an inequality statement, M1 is greater than M2. You lost mass. All right? So that mass that you lost actually can be converted to energy according to Einstein's famous equation. Energy is equal to mass. And what does C stand for? Anybody know?
Carbon?
Not carbon here, the lowercase c.
Oh.
The speed of light.
The speed of light, yep. Mass of of what's converted times, this is the speed of light. Yeah, I guess I did have it down here, which is a relatively large number. So if you take this number, 300,000, and you square it times the mass that you lost during fusion, that's fusion, by the way, nuclear fusion, okay, then that's equal to the energy that's formed. And we'll talk about it. It's kind of staggering. Now, all stars are doing this. All active stars have nuclear fusion going on only in their cores, because that's only where it's hot enough and it's most dense enough. I guess I'm going to have to backtrack on that later, but in general. All right. Now, this slide kind of snuck in there. I got to this slide, I was preparing for class, I'm like, did I really include that slide? This is actually fast forwarding to the end of the course when we want to talk about kind of the unfolding of our universe, the creation of our universe. We're going to see that our universe started out as what we call a singularity, something very small, and it was pure energy, and had no matter. And I know it's kind of strange, but I'm going to put up Einstein's E is equal to mc squared. And I just described how we can take matter and convert it into energy. At the time of singularity, at the time of the universe, the Big Bang, it actually took energy and converted it into matter. But anyway, we're going to talk about kind of the formation of our universe and how these four forces that you see today, of course, you're kind of familiar with gravity. Do we know everything there is to know about gravity? No. But Newton's laws of motion, universal law of gravitation, kind of sums up how it behaves. Electromagnetism, strong force and weak force actually has to do with kind of the atom. So those are the things that we need to ultimately talk about. So yeah, these will be we're going to go on to the next chapter too. The next, it's because they're not called chapter, the next lecture part. So how many of these do you guys need to do? Just three of these? Yay! Okay, so those we do when we meet again on Monday. Monday. This next part is a little less taxing. Let's see if you think so too. A lot of this stuff I feel like we've already kind of touched on. Kind of got a mind of its own right now. Okay. So this is a picture of an astronaut that is manhandling and you kind of see the scale of the Hubble Space Telescope, affectionately called the HST, the Hubble Space Telescope. So cool. The Hubble Space Telescope orbits the Earth from pole to pole about every 90 minutes. And if you're out at the observatory, there are times, and anywhere, don't have the observatory, there are times when actually you can see the Hubble Space Telescope go across the sky. Maybe I'll be talking more about that. If there's any upcoming events, I'll kind of let you know. And the way you see it is not by like, oh, I can see that. What actually you will just see are the solar panels or the antenna that are reflecting the glint of the sun back to your location. So it's very location specific if you see the Hubble Space Telescope.
But it seems kind of like a shooting star or something just because it's moving so fast?
Well, shooting stars, and they go, shooting stars are the meteors, right, that are kind of going through the Earth's atmosphere. You call them shooting stars. Those are usually faster than this. Once you've seen a few of these, the passes, you're like, oh, I understand that. It's called a cadence, I guess. I kind of understand that. And so to me, the meteor things are faster. But okay, so all right, synchronous rotation. I'll be talking more about this. I brought in the other day. These are my moons. Woohoo! Sun, right? Still made up. Sun. This works. So, do you guys remember? Let's see. I'm going to do it this way. I'm going to take this one first. Okay. So, what does that say? It's supposed to say sunlit. Very good. Sunlit side, and then this is my not sunlit side. Okay. So my sunlit side needs to go like that. Does that make sense? So do you guys remember how long I said, wait, first off, what kind of moon is this? If I'm the Earth and this is the moon, full. I heard somebody say full. Very good. It is a full moon. Perfect. And now I'm going to go ahead and I'm going to do, I better go counterclockwise. Am I going counterclockwise? Yes. Yes, good. I'm going to go ahead and do this. Do you guys remember how long this takes? It's a nice even.
2 or 3 months. Right?
Nope.
No, that's.
No, that's something else. 3 months is something else. No. Well, here's one for you. How long does it take for the moon to do this one time? About a month. Very good. So take a month and divide it into 4. About a week. About a week. Okay, about a week. So what phase is this? New. Very good. About a week. Last quarter. About a week. Full. That's it. Now, you guys have probably heard, and I'm kind of going to talk about it later on a few slides later, but have you heard of this kind of the far side of the moon? Okay, sometimes it's called the dark side, and it really shouldn't be called the dark side. It really shouldn't. But we only see, and I'll show you later the differences between what they look like, we only see one side of the moon. And the reason is because of something we call synchronous rotation. Now, if you are in sync with something, that means you're like with them, one and one. The in sync part of synchronous rotation looks like this. Okay, so what does this say?
Oh, near side.
It says near side, very good. And? Far. Okay, so she said near side and far side. This is the side of the moon we don't see. This is the side of the moon that we do see. The far side is far more ugly than the near side. Okay, so here's how this goes. And I'm gonna just show you, and there'll be a slide to kind of show you again. Synchronous rotation means that, well, first off, the thing that's in sync, yes, is you guys told me it takes a month to go around, right? It also takes a month, actually 29 and a half days about, for it to rotate once on its axis. So as it's orbiting the Earth, it's also, and you probably can't tell it because it's a very subtle thing, it's also spinning on an axis of rotation. Spinning on an axis of rotation, spinning on an axis of rotation, spinning on an axis of rotation. So once it comes back to complete the phase, it has rotated once. That's it. So we only see this side. And other planets with moons, it's called being gravitationally locked, okay? And it's an in-sync sort of thing that happens between a planet and its lovely moon over the course of time. They are tidally locked. Gravitational tidally locked. So that's it. Sounds like I saw some nodding. So we're going to talk about the moon, but is the Earth always the same distance from the sun? And I kind of butchered this the other day. I screwed my terms up. When the Earth is closest to the sun, starts with the letter P. What do we call that? Perihelion. Thank you, perihelion. When it's farthest from the sun, we call that aphelion. Perfect. Well, we kind of have a similar thing going on with regard to the moon. I'm going to go ahead and take these terms. Perigee is like perihelion. Apogee is like aphelion. So notice we have the center here is the Earth, and this is kind of the moon's orbit. So here at a distance of 356,000 kilometers, I'm going to put perigee. And yeah, that's right. And I'm going to put apogee here. Sometimes I misspell it, apogee. All right? Cool. That works. So you might have heard these terms before, and I didn't look them up, when is our next supermoon, but you probably heard of the supermoon thing. And all the supermoon means is it is you guys told me that this is a full moon, okay? Sunlit part. So a supermoon is when two things happen. You get full moon, and it is at perigee. That's it. Mini moon is when you get a full moon, and it's at apogee. I didn't used to know the word mini moon, but it caught my eye. It's so cute. Okay? That's it. And I think you guys look pretty convinced that the only reason we see the moon, there's no nuclear fusion going on in the moon. It's not hot. Okay? It's just the reason we see it is because of the sun. Cool. And this is actually, the caption here said this was taken by a satellite. And can you see, probably hard for you to see, but we must have the sun over here, and it's shining on the moon, and the sun is also shining on the earth. So you can kind of see the daytime side of the earth and the nighttime side of the earth. Cool. So this is what we've been talking about, and we've been looking at it firsthand this week. This idea of the moon going through different phases. The moon's now getting closer to the sun. Okay. Let's see if we can find what the moon looked like. Waning crescent. Probably, hopefully, the moon kind of looked like something like that right now. And here's the sun over here. It's on its way. Okay. And then, it's about a week. Are we okay with this? This is 1 week. This is, I don't know how you want to, I called it first week. Okay. But it takes a week to go to each one of those phases. Cool. All right. So there are some terms, and you're going to want to, and you might even, on your note card, you're going to take your test next Monday. You can have a, 4x6 this semester? Okay. 4x6 note card. Again, if you're thinking note cards, you don't have to go out and buy one if you don't want to. You just take a piece of paper, your favorite color card stock, make sure it's 4x6 and write on it. What I started to say is you might want to go ahead and make sure you add these kind of phases. So as it starts with a new moon, oops, wrong one. As it starts with the new moon, okay, this is where this is full. It's over here. Starts with the new moon, okay. We begin to see more and more of the illuminated side. Okay, that process is called waxing. So waxing simply means you're seeing more and more of the illuminated side. So if we think about it this way, it's going to actually wax from what? From new to full, because it's going to keep seeing more and more of it, right? Now the process on the other side, which is where the moon is right now, is we are going to see less and less of the moon. That process is called waning. Wax on, wax off. Okay? So this is called waning. So in between, from waxing and waning, we have some terms. If it's less than a quarter, we call it a crescent. If it's more than a quarter, we call it a gibbous. Okay, gibbous, crescent. That's how that kind of goes. The whole quarter thing, and I kind of mumbled something about it, kind of gets on my nerves because you're like, to me, it's like a half instead of a quarter. So we'll call this first quarter, and I've called this last quarter because I can never remember. I think it's also called third quarter or last quarter. Are there any questions about all this? And all this time, we're seeing the same near side of the moon.
So this is kind of a silly question.
There are silly questions.
Does every continent see the same side of the moon?
I had that question recently. And if we kind of think through it, let's go full moon, right? And then think of the Earth spinning. So you know that everybody at our latitude will see the moon actually at the same angle.
Right.
And if you're in the southern hemisphere, you're going to see the moon kind of at a different angle, but you will see the moon in the same phase. Yep.
Because the Earth spins faster than the moon spins.
Right, the Earth takes 24 hours, right. Yeah, and then the moon's like, Yep. Very good. So this slide only adds one new thing, and that is the term terminator. I'll be back. I know, right? So the terminator, I'm going to draw the terminator on all these little cute little slides of the moon. There's the terminator, here's the terminator, here's the terminator, terminator, and the thing that those all have in common is it's where the illuminated side from our perspective meets the dark side. Yep. And the cool thing, or if you're out observing, like with a telescope or even with binoculars, it's that intersection that you're going to see your coolest features. Because actually then you start to see kind of craters that are kind of bumpy. You start to see some shadows and some light. It is so cool. Well, we will pick up here and do more slides. Also on Monday, I had a constellation of the week, and I'll bring that on Monday. So we'll just see how far we get Monday, Wednesday, Friday, and then take your test the following Monday.